Welcome back to Computer Science 3200. Today, we are looking at hash functions and hash tables. It's a bit of a departure from the search-related stuff that we've been doing. We're going to do some hash tables and hash functions, and at the very end of this lecture, I'll let you know how you can actually use that in your assignment if you haven't sort of figured that out already. Then, in the next couple of lectures, we're going to get into a bit of game theory. And then we'll get back to some search with some two-player minimax search, and then after that, we'll have the midterm after that. So today we are talking about hash functions, and they are very, very useful and very interesting to me. So I'm excited to get to tell you a little bit about hash functions. So let's get the lecture going here. Okie dokie. So hash functions and hash tables. What are they? Why do we care about them? How are we going to use them? Well, let's find out. So what is a hash function? A hash function is a function, obviously, and it's used to map data of an arbitrary size to data of a fixed size, typically. So we're going to take some sort of input data, and we're going to map that data into some sort of output data. And typically, depending on the use case, that output is going to be a fixed size. So an example of that might be taking in a name or another string and then doing some mathematics on the digits of that in order to produce an integer which is related to that string, okay? And values that are returned by hash functions are called different things, but usually we call them hash values or hash sums or hashes, okay? So the hash of a string might be some integer value. Now, we don't always have to convert our data to an integer. However, typically it is converted to an integer in the end. Hash values are very commonly used as an index into a lookup table or a hash table. And we'll talk about that in a little bit. But essentially what's happening is that we're going to take some input data. Here we have, again, a string as an example. That string is going to be passed through a hash function, and it's going to output some sort of hash value or hash sum over here. And we can see that in this example, we are producing a fixed length output from a variable length input, okay? So that's an important property of most hash functions, is that, say, we want to pass in an arbitrary string, we pass it through a hash function, and then we get like some 32-bit integer or 64-bit integer or whatever out the other side. And we can see here that for some hash functions, like for example, this string here says the red fox runs across the ice, and this one says the red fox walks across the ice. For some hash functions, like these two strings are quite similar, but they produced vastly different outputs. Okay, and some hash functions, we will want that property where small differences in the inputs produce big differences in the output. And sometimes we won't want that property. We will want small differences in the input to have small differences in the output. And that depends on the use case, as we'll see in the future. So what are some uses for hash functions? The first is data retrieval and data storage. So we can use hash functions to quickly find data by computing an index or a key for a hash table. And we'll talk a lot about hash tables in the second bit of this course, bit of this lecture. Data protection. So for example, we could store a password hash so that the original password cannot be retrieved. So many people, maybe you're not aware of this fact, but if you have a secure way of logging into a website, for example, let's say over here, these are different passwords. So this one is Fox, this one is a bit longer, this one is the same, like almost the same thing, but has a few characters different. So let's pretend that these are passwords, okay? So the way you do proper security for your login system is that you don't store the password in plain text. You store the hash value of the password in plain text. So what this means is that when you go to log in, all you have in the database is the hash value, okay? So someone types in their password, you can pass it through the hash function, and then out of that, you get, they go to log in, they type in their password, you hash it, and whatever they typed in for your password, you compare that to the hashed value of their password. Now, these hash functions, typically, the good ones anyway, are very unlikely that two different inputs will produce the same output. So it's a way of kind of scrambling up your password so that the password still means something, you're still using it for verification, but if someone hacks into your system, all they're able to see is this hash sum and not the hash password. So even if they do get the hash sum, they're still not able to log into the website, but the website is able to use the hash sum as verification for login. So that's one thing that it's used for. So data protection. Also, it's used for data verification. So we can hash large amounts of data to smaller checksum values that can later be verified. So this is used all the time online to actually verify a download. So let's say, for example, that this string here is actually like a gigabyte of data, right? So how is it possible for me to send you a gigabyte of data online and make sure somehow that the bits that I was trying to send you are the exact bits that you received? Okay, that's an important problem. You don't want to send me some like nuclear launch codes or something like that and have one of the digits be wrong. So one way to do that is that you take your large data, you're going to run it through a hash function on your local machine where you know the data is correct, and you produce a hash sum out of that, or a checksum that they're called for data security or data verification. So I'm going to send you the data and I'm going to send you the checksum value. And on your side, you're going to run your data that you received through the same hash function. And if you get the exact same checksum, then you know, like beyond a statistical probability, that the data that you received is actually the data that was sent to you. And so that's another use for hashing that's very important, is data integrity, data verification. And also, I mean, there are dozens of uses for hash functions, but just another one to show you that they are quite useful is geometric hashing. So it's used for proximity-based problems in computational geometry, and it turns out that geometric hashing is kind of related to our assignment. So you combine geometric hashing and data retrieval, and we'll be able to show you how to make like a really cool closed list that has really nice properties, for example. Okie doke. So for container membership query, that's something that hash functions are often used for. So the open and closed lists in your assignment, the membership in the closed list is one of the most common queries in search, right? We're going to keep a list of things that have a property, and the property here is that they're in the open or closed list. So how you store the open and closed lists matters for membership queries. So for example, if you used a list or an array and you wanted, like, so you're going to have a list of all the nodes or a list of all the states in the closed list, right? So that's what you did for assignment 1. You just had an array of those. And then to see whether or not a certain state was in the closed list, you looked through all the states in the closed list to see if the one you want is there. And so that's O of n membership query, because you have to check the whole thing where n is the size of the list. If you have a set or a dictionary that's based on like a binary tree or something like that, or a heap, then your query time is going to be log n. Hopefully you studied that in your algorithms course. With a hash table, okay, just an arbitrary hash table, in the worst case, it's going to be O of n, and we'll talk about why that is a bit later. But if you could come up with what's called a perfect hash table that has a one-to-one mapping between your data that you want to hash and actual index values in your hash table, then you could do this in constant time. So it would be O of 1 lookup in the worst case, which is the ideal case for us. Okay, so hash tables, what are they and how do they work? So to hash a data structure means to represent it in another, typically fixed or simpler form, right? So hashing is going to be done by a function that turns some sort of data structure, whether it's a string or a more complex thing, into a number. And integers are preferred as the output number, the result of the hash function, for several reasons. So, well, A, we always want to work with integers because computers store and handle integers very efficiently. And also, and we can manipulate integers really efficiently in many ways using bit operations and stuff, which is also really nice. And we can also use integers to index an array of data. So if we're indexing an array of data, then that's called a hash table, right? So if we've hashed our value into an index, and we're then using that index as the index into an array, then that array, we are calling this whole system a hash table. So what is the input to a hash function going to look like? Well, a hash function is going to expect data in a given format, right? So for example, we might say the input is going to be a string, or the input is going to be a double, or the input is going to be, I don't know, an image file in the JPEG format or something like that. So it's going to expect data in a specific format. Hash functions may also expect a given range of values from a particular input format. So it may say, for example, the input is going to be a floating point number between 0 and 1, or the input is going to be a string whose maximum length is 64, or it's going to be a file, and that file is going to be like at most a gigabyte in size. Typically, a hash function does have some sort of notion of the input. So hashing an unexpected input value, or a value from outside the expected range, may produce poor or undefined results. So that just means that if you've designed a hash function to input a number between 0 and 1, and you give it 100, specific hash functions may be designed with that input range in mind, and if you don't pass in a number, then who knows what you're getting out the end. Maybe it's not cryptographically secure, maybe it's not the value that you expect it to be. So for example here, just to have it on the slide, an example might be hashing a string into an integer value. And almost more important than the hash function input is the hash function output. A hash function is typically going to produce values in a predefined format and a predefined range. And this is really important because the output integer, typically, is often going to be used as an index for an array or a lookup table, right? And so we need to, if we have an array of a specific size, then we don't want to have values that are output that are like bigger than the table, because then we'll get our program crashing, index out of bounds, and all that kind of stuff, right? Integers are convenient as the output to hash functions because we can easily restrain their output range, right? So let's say, for example, my hash function outputs a number between 0 and 1,000,000, but my hash table is only 1,000 long. Well, I can just modulus 1,000,000 by 1,000 to control the output range, right? So integers are really convenient for that purpose. All right, so now that we know what goes into a hash function and what comes out of a hash function, what are some of the properties of a hash function that we can actually measure, like statistically? So the first one is determinism. So a good hash function should not be random, right? So every time we run our same data through the same hash function, ideally, we're going to be given the same output value, right? So that means that, like, if I hash my gigabyte of data that I'm trying to send you, there's no randomness in that function. So that when you run it on your computer, you want to get that same value for the same data. So determinism is typically a good idea when it comes to writing a good hash function. Uniformity. A good hash function is going to map the range of possible inputs as evenly as possible over the output range. And what that's going to do is it's going to help prevent expensive hash collisions. And we'll talk about, and a hash collision is just when two inputs are mapped to the same output value. So for example, let's say we were trying to hash a large number into a smaller number, right? And all we did was the hash function just said the output is 0 if it's even, it's 1 if it's odd, right? And so, okay, that's the range of output value. Sorry, that's the next example I'm going to give. Let's say, for example, we just said the hash function was like everything is 0, right? That's useless. We want to have some output range, and ideally, our output range is going to be uniform. And there's all sorts of security risks involved with non-uniform hash functions, etc. The output range. Also, it's desirable to have a defined range for the hash output, as well as like sometimes you want it to be a fixed width, for example. So you may want to say, okay, the representation of my output is going to be a number between, let's say it's a 32-bit number, but I'm going to make sure to pad it with zeros or something like that, so that it's like a defined output range and a fixed width of display for the output range. So determinism, uniformity, output range. Also, data normalization. So you may be interested in normalizing your data. So for example, sometimes your input data is going to contain features that might be irrelevant to the context that you're trying to hash your data in. So let's say we were trying to hash student names, right? So student names into some lookup table, maybe for like a phone book or something like that. So someone passes you in a name that's capitalized, someone passes you in a name that's not capitalized, maybe someone had typed in all caps, right? Maybe we just want to throw away upper or lowercase letters and normalize that data so that no matter whether it was uppercase or lowercase, it's going to hash those names to the same value. So that might be a property that we're interested in. However, there might be some cases where that upper or lowercase is critical information, right? Maybe it's the name of a file or something like that, which is important. Continuity. So we talked about this a bit before. So do small changes in the input values result in small changes in the output values? Sometimes we want that, right? So let's say we're hashing something geometric. So we're hashing the location inside a map or an environment. Well, maybe if I'm at a current location and I hash that value into an integer, and then I move just slightly to the left, I want that hash value to somehow be close to the hash value of the previous position. Sometimes. However, in cryptography, I would not want that to happen. Like, if I type in a big password like 64 characters, even if I have just one character change in my password, I don't want my hash outputs to look anything alike. Because if they do look alike, then you could like reverse engineer it or crack the cryptography somehow, and that's not good. So sometimes when we're talking about like security applications, we don't want any continuity. We want the output to almost look random, right? But sometimes in very specific circumstances, we want it to be continuous. How about reversibility? So some hash functions are invertible. So we can obtain the input back from a given output. So that might be desired for cases like geometrical hashing, or if you're trying to store things in the closed list, for example. But sometimes you absolutely do not want it to be reversible, right? So if you're talking about password hashes, you definitely don't want that to be reversible, right? You don't want someone to be able to hack in and get your password hash and then figure out what your password was from the hash. So non-invertible functions are also called one-way hash functions. So what are some hash function algorithms? Okay, well, we could have things like trivial hash functions. So trivial hash functions are something you might come up with in like grade 3, right? When you're trying to play a spy or something like that and turn your name into a secret number. So a trivial hash function is when some sort of typically small data can be directly translated into its hashed value. So for example, if you have a character like A, B, C, D, and you just one-to-one map those into integer values. So A is 1, B is 2, C is 3, etc. Right? So you're doing up a secret code for your secret crush in elementary school or something like that. That's a trivial hash function. Okay. You could also have a perfect hash function. And so if we remember I'll show an example of this. An injective function is where each possible input maps uniquely to a value in the output range. And this is called a one-to-one function, and also called a perfect hash function. All right, so here are properties of hash functions, of specific algorithms of hash functions. 1, injective. And you may have flashbacks to your math or logic course looking at these slides, but they're very important when it comes to hash functions. So an injective function, each input maps uniquely to an output. So some of the output values may be unmapped, right? Injective functions typically can be made invertible. So, for example, when I talked about mapping a letter of the alphabet to an integer, right? So each letter of the alphabet can be easily mapped to an integer just by going up 1 for each letter. And so depending on how we map the output value, so let's say we say, I'm going to map a letter of the alphabet to a number between 0 and 100. That is still injective because each input maps uniquely to one output value. However, the values 27 to 100 are just going to be not mapped to anything, right? And since injective values have unique outputs, it means it's possible that they could be made invertible. So you could say, if I give you the number 4, you can say, well, that's D, right? Because you know how that function works. Surjective. So surjective means that for every possible output value y, there is at least one input value x such that f of x equals y, all right? So in general, surjective functions are not invertible. And we'll talk about why that is when I get to an example. So this isn't correct. Most surjective functions are not invertible. Okie doke. So, bijective means that the inputs and outputs map uniquely. All right? So if, one second, I'm going to put that back in. So the inputs and outputs map uniquely one-to-one. Sorry, I'm going crazy here with the controls. So from math, someone in the chat just said this. In math, 1002 or CS 1002, that is one-to-one and onto. And this is also called a minimal perfect hash function. So if you remember back to math, right, the way you test for injectiveness is you draw a horizontal line across your function, and if any horizontal line touches the function in exactly one place, then it's injective. Okay? If your horizontal line touches in multiple places, then it's not injective because it does not map uniquely to a single output value. Okay. Here, for example, we have like a dictionary or a phone book. So here we have the keys that we want to hash. So we have John Smith, Lisa Smith, Sam Doe, Sandra D, right? All of these names here. We're going to pass these names through our hash function. And here, for example, John Smith is going to turn out to be 02. Lisa Smith is 01. Sam Doe is 04. Sandra D, 02. Uh-oh. So if I ask you on an exam whether or not this is an injective hash function, what are you going to say? Well, you're going to look back at the property of injective. Each input maps uniquely to an output. Well, John Smith and Sandra D do not have unique output mappings. So this is not an injective function, okay? And you can see here now, in the hash terminology, this is going to be called a hash collision. And if we're going to be using hash functions to compute indices to store things in arrays, you can see how hash collisions are going to be a problem. Because then it's like, oh, how do I actually store that data if there's something already there, right? So we'll talk about that in a few minutes. So blatantly taken from Wikipedia because these are great examples. Here are some function properties, right? So this function, the inputs map uniquely to outputs. However, there are some outputs that are not mapped. So the inputs map uniquely to outputs, so it's injective, but there are some outputs that aren't mapped, so it is not surjective. Okay? This function is injective because all the inputs map uniquely, and all of the outputs are used, so it's surjective. Okay? So this is an injective and surjective function, so it's bijective. This function, we have 3 and 4 being mapped to C, and so the input mappings are not unique to outputs, so it is not injective, but all the outputs are mapped, so it's surjective. It's not bijective, okay? That's an important difference. Bijective has to have unique mappings to unique values. And in this one, we have neither property, where we have non-unique input mappings, and we have outputs that aren't used. So that is not injective, and it is not surjective. Okay, so here are some simple hashing functions, some simple examples. One is just modulus hashing. So let's say that I want to take an integer value of any size and turn it into an integer between 0 and 10. Okay? Well, how am I going to do that? Well, I'm going to have my hash function h here, int h. It's going to take as input an integer x, and it's going to return x mod n. And the modulus operator is essentially the remainder after division. So if you've never used mod before, here's how mod works. Let's say I have n is 4, so n equal to 4. And let's say I want to take the number 11 and modulus 4. So what I essentially do is I start counting here, right? And I go, it's division with remainder. So we'd have 0, oops, I gotta use my thing. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 0, 1, 2, 3, 11 mod 4 is equal to 3. That's how you do it. You divide and you take the remainder. So for example, let's say we want to map the values of 0 to 1,000 into 0 to 10, right? You can do this. And this acts as a sort of truncation. So it only really cares about the lower order bits. So the way to think about that is, now you can't do this. You can only do this trick if you're doing mod 10, okay? But let's say I take the number 1264 and I do mod 10. Well, because this number is in the base 10 number system, all I'm really looking at is dividing by 10 and taking the remainder, which is going to be the last digit. Similarly, if I modulus by 100, I'd be dividing by 100 and getting the remainder, which is 64, okay? So you can look at this, and this is why we're saying this is kind of a truncation, because we discard the higher order bits, and we only care about the lower order bits. And be careful of uniformity issues if x is not a multiple of n. So if the range is not a multiple of n, you may get non-uniform hashing. So what does that mean? It means that let's say our range is going to be numbers between 0 and 5. And our output range is n equal to 4 right here. Oh, sorry, there's a 5 up here behind my head. So let's look at this bucketing system here and see how all of the different values from 0 to 5 map into n equal 4 with modulus. Well, we've got 0 is going to be here, 1 is going to be here, 2 is going to be here, 3 is going to be here. We're just modulating 4. 4 is 0 mod 4, and 5 is 1 mod 4, okay? So we've got double the number of hash values going into slots 1 and 2 than we have going into slots 3 and 4. So this is not a very uniform hashing scheme for certain values sometimes. Now, as your range gets larger, right, this effect sort of calms down. It evens out more. but just to let you know that it may cause problems with uniformity. We could also do something that's called binning, and binning is almost the opposite of modulus. So binning is just going to do division instead of modulus. So over here again, let's have 4 bins, right? And we're going to map, let's say, the number 12 into this. So what do? We take 12. Oh, actually, what do I want to do here? Yeah, n is not the number of bins here. N is some other value that we have that is well chosen for this purpose. So we're going to take our input range and basically divide it by the number of outputs that we have, right? So let's say my input range is between 0 and 100. Then I have 100 over 4 is going to be the number that I divide to. So 0 to 25 are going to go in the first bin. 26 to 50 are going to go in the second bin. 50 to 75 are going to go in the third bin. And 75 to 100 are going to go in the fourth bin. So you could see that, like, if I had a bunch of small numbers, they're all going to go in the first bin, and maybe this is not overall super uniform, right? However, as the limit increases to an infinite number of values put in, these both are uniform. But you might want to use one in one case and another in another case. They're just examples of simple hashing functions. Let's look now at string hashing. All right, so let's consider the string Churchill, which is my last name. So let's hash that. What is one possible way that we could hash the string Churchill? Well, let's just sum up the ASCII character values, all right? So if we look at the ASCII values over here, we're going to sum up all of the ASCII values of Churchill, and we'll get 926. So with that function in mind of just summing up all the hash values, I'm going to ask, is this, so let's ask the chat, is this injective? So in the chat, type I equals true or I equals false. Is it injective? Is it surjective? Type S equals true, S equals false. What about distribution? Is this evenly distributed? Okay. What do you think the distribution will look like? Is this reversible? Well, let's talk about that now, okay? So let's see. Is this function injective? Meaning, okay, so people are saying I equals false, S equals false. So let's have a look. Injective means that all possible inputs uniquely map to outputs. Well, a good way to prove that something isn't injective is to come up with a counterexample, right? So if my name was Bob, right? Or if my name was Ob, stupid example, but B-O-B, those numbers sum to the same thing as O-B-B, right? Someone else in the example, in the chat, just came up with an example. What if I lowered the L by 1 to become a K? And if I increased the L by 1 to become an M? That's a good example. So this would be 1 lower, this would be 1 higher, so it would cancel each other out, right? So Churchicum would hash to the same thing as Churchill, so it's not injective. Is it surjective? Meaning, are all the possible output values covered? Everyone said false in the chat, but I would say that if you choose any integer value, I could come up with a string that summed to that value, right? You just have that many A's, for example. Well, if A was 1, you could do that. So I would claim that this is surjective, because for any possible output value, there is an input which maps to it. There's just not a unique mapping. So it is surjective, but it is not injective, okay? Now, we're talking about positive integers, of course, right? because ASCII values are positive. The distribution. It turns out that for strings of the same length, this is not evenly distributed. It kind of looks like a normal distribution. Okay? And the reason for that, or for random strings of a given length, all of the values kind of even out to be sort of in the middle. So it's almost like rolling 2 dice, right? The values that are possible for rolling 2 dice are far more skewed toward getting 7s than they are at getting 2s or getting 12s, because there's more possibilities for that. See how that works? Okay. So the distribution is not uniform, and it is obviously not reversible. Because if I gave you the number 10 and said, give me the string that hashed to that, well, it could be, what's the 10th number? I? J? Something like that? A, B, C, D, E, F, G, H, I, J. So it is J. So it could be a J. It could be 10 A's. It could be DDB, right? It could be a number of things. So it's not reversible. Okay. And the input character order doesn't matter, because we just saw that any anagram of Churchill, any anagram of Bob, any anagram of any word will sum up to the same value. Okay. So what some people do is they do something called block summation. And block summation, there are many different algorithms that work on blocks. Some of them are very secure, some of them are not secure. So let's take blocks of n characters at a time, and we're going to interpret those blocks as a single longer integer. And so 4 1-byte characters is going to equal 1 4-byte integer. So we're going to sum the resulting integers. So let's take blocks of 4. So we're going to take CHUR, and CHUR is 192, 20, or 29, 97, 27, something like that. Then we're going to take CHIL, and we're going to figure out the value for that. Then we're going to take L, figure out the value for that, and then sum the blocks. Okay? Then if we use the hash table, for example, we could modulus this with the hash size. So the hash of Churchill, now, it would be different than other anagrams of Churchill. However, they're like churl would hash to the same value, right? So we're getting a little bit better, but it turns out that a lot of really good hashing functions that are more secure, they do lots of like bit fiddling and block summation and stuff like that. So this is sort of like on our way to a better hash function. What about geometric hashing? Well, here's an example of that, because I've mentioned this a number of times. So it's very common that we would have our hash table implemented as a one-dimensional array, right? Just a normal array. However, in our assignment, we have a 2D array for example, our map, right? Or for our closed list. So what we want is to take the index in a 2D array, so the XY value in a 2D array, and we want to convert it to the index of a one-dimensional array. And let's do that. So let's take the input XY, and we want to output I. So let's just look at that as a problem. So here we have a 2-dimensional array. Please bear with my unsteady hand. Okay. And we want to take that 2-dimensional array and map each of those cells into one of the cells in a one-dimensional array. And of course, we're going to pretend that these things have the same number of cells, obviously, right? So the easiest way to do that is maybe just go along the top, right? So I'm going to map this one to this one, this one to this one, this one to this one, this one to this one. Now go to the next row. This one to this one, this one to this one, this one to this one, this one to this one. And there is a formula for that. So if our hash function is y times width plus x, So here, for example, let's take 1, comma 0. Our width is 4. So we have 1 times width, so 4 plus x, which is, oh, sorry, this is 0, 1. I'm an idiot. Sorry, 0, 1. Y times width plus x. Y is 1, so we get 4 plus 0, so that's index 4. And if we look at this line, this is 0, 1, 2, 3, 4. So that's the mathematical way of doing this one-to-one mapping that I showed you. And this is injective because every input value in the 2D array has a unique value in the 1D array that it maps to. It's surjective because every value in the 1D array has a value mapped to it. And that makes it bijective, so it's it's one-to-one and onto. So it is a minimal perfect hash function. And it's also reversible. If we take the index I, we can convert I back to the index in the 2D array. If we divide I by the width, we get the row, which is Y. And if we mod I by the width, we get the column, which is X. Okay, so for A star, we can use a one-dimensional Boolean array as the closed list if we want to be like optimally efficient for storing the closed list. And this is how you can map those values to each other. Cool. Now, we talked about hash collisions a little bit. What are they? Why are they bad? Why are they the bane of our existence? And they are the bane of our existence. So hashing data to an integer is typically used to index a hash table, right? We're going to see that in the future. If an array of a particular size n is used, then the hash function typically finishes with like a modulus n operation. And that just means we're taking the output of the hash function, however complex it may be, and then fitting it somewhere inside the length of our array. So a hash collision occurs when two inputs produce the same hashing output. And that's going to cause a collision, meaning two things are trying to occupy the same space inside the hash table. So let's look at hash collisions. We saw this example already in the class. So let's hash some names, right? So John Smith goes to 02, Lisa Smith goes to 01, Sam Doe goes to 04, Sandra D goes to 02. So whatever hash function we used took John Smith and Sandra D and produced the same output value. Now, you might think that like, oh, but we're using a cryptographically safe hash function. That's not really going to happen in practice. Well, for many, many years, people thought CRC32, which was a popular hash function that's no longer used for anything secure, was very, very secure. And so what this did, it took in a string and it produced a 32-bit integer. And someone found out that there were a bunch of actually pretty common English words that produced the same hash value. It was terrible. So plumless run through CRC32 gave the exact same output hash value as buckaroo. Now I know, okay, plumless and buckaroo, maybe they're not the most common words, but they're like actual English words that gave the same hash value. So whoever made CRC32 didn't even run it through the dictionary before they released it as a standard, which is kind of bad. So now what happens is we have like our cryptographically safe hash functions are like, they produce like 1,000 bits rather than 32 bits of output. So what happens? What do we do when this happens? Are we lost? No, we can do some things. So if two values collide, how do we store their values in the hash table? Well, it turns out that there are solutions, but they're all expensive, okay? And expensive meaning they're going to involve some calculations, and that's all you can do. Sometimes, if you don't have a perfect hash function, it's just going to be an expensive solution. But first, let's talk about, before we design a solution to something, we want to know how often that thing occurs, right? So let's look. Hash collision probability. So this is the birthday problem, or the birthday paradox. What is the probability with n people that 2 of those people have the same birthday? It turns out that you might intuitively think, okay, well, there's 365 days in a year. So to have a 50% probability of 2 people having the same birthday, you're going to need 365 divided by 2, right? No, that's not the case at all. And the reason for that is the following. Let's draw an example. Let's say this is all the possible birthdays. Okay? So that's 4, 5, 6, 7, 8. So let's say there's only 8 days of the year because we actually, I can't draw 365 things here. So let's take my birthday. My birthday falls on day 3, right? So there was a 0% probability of the first person, of one person having the same birthday as another, right? So my birthday is here. All right, so I'm blocking this one off. Now, let's take the second person. So there's a 1 in 8 probability that the second person has the same birthday as me, right? So let's say they don't, and their birthday falls right here. Now, the third person, oh, look at this. What's the probability that the third person's birthday is the same as someone else? Well, there's 8 spaces, and there's 2 already used up. So there's a 2 over 8, or 1 in 4 chance already that that person has the same birthday. Okay? So it gets very quickly to the point where you're going to cause hash collisions. So if you have, let's say, 100 people, right? Oh, sorry. Down here, we have a graph. Oh, I don't have my laser pointer. Here is a graph of the birthday problem. And if we have this many people, here is the probability of 2 of them or more having the same birthday. And it turns out that at 23 people, there's a 50-50 chance that 2 people have the same birthday. And why, Dave, who cares about birthdays, right? Well, the birthday problem is the hash collision problem, right? Because people essentially have random birthdays. So this teaches us something about hash collisions. So with each new hash that we do, the probability of hitting a previous hashed value rises. And so a kind of general rule, it's not exact, but we're going to have a 50% probability of a hash collision at approximately the square root of the output range of values. So if we have a 32-bit integer, let's say we have an array that can hold all possible 32-bit integers, so all 4 billion values, right? You might say, well, there's 4 billion values. We're not going to have a hash collision for a long time, right? There's only 30 million people in Canada. We'll never have a hash collision of 4 billion, right? The chances are so low. However, it's the birthday problem, right? So we have a 50% chance of there being a 32-bit or 4 billion possible value hash collision at 70,000 hashes. And at only 250,000 hashes, you have a 99% probability of there being a hash collision. So even if you have a really, really big array, you're still going to run into hash collisions after just like several thousand inputs. And that's assuming a random distribution. We don't have a perfect hash function. So hash tables, also called hash maps or lookup tables. Hash tables are data structures that hold data, and they associate some data with a value via a key or an identifier, right? So you might have hash function of data equals key. So this data might be a name like Sandra D, right? We turn that into a key. Maybe it's an integer. And then in our hash table, we look up the value, or we look up the key as the index, and that gives us the value. That can be implemented in many, many ways, but the most efficient and the most common is usually just using an array. And Python's built-in dictionaries use hash tables, by the way, if you were curious how they work. So hash tables can serve, this is like kind of an aside here. Not only can they store data, but I like this example of like another use for a hash table that you may not expect. Hash tables can serve as a cache to save relatively expensive computations. This is sometimes called memoization. Hash tables enable programs to use additional memory to gain speed. So ideally, hash table query time is independent of the number of total entries. So you don't want your hash table to just be a list, right? Because that means if it's a list, every time we add something to it, it's getting more and more expensive to look up next time. So if we have a good hash table with a fixed size, this can be really important. So let's look at this. Here we have a class written in Python. I know this course is not in Python, but a lot of people know Python. This is a memoize class. So we're going to, as the instructor, for the constructor, we're going to be passed in a function. So we're going to record that function as self.f, and then we're going to have self.memo be a variable, which is an empty dictionary, okay? And whenever we call this function, we're going to look up whether or not the arguments to that function are currently in the dictionary. If they are, we're just going to look up the value. Otherwise, we're going to compute the function. And it's really easy to do this in Python. So we can just have like define factorial k, and then instead of just calling factorial, we call memoize on factorial. So what in the hell is this doing? Why do we care? Well, somewhere in its memory, in its dictionary, Python has a hash table, okay? So we're going to call some expensive computation. Let's say whether or not this is a prime number, okay? So like some really, really long number, is it prime? That is supposed to be a question mark. I apologize. So is this big long number prime? So what this does is it's going to hash the big long number, look it up in the internal dictionary, and if it's not there, or if it is there, it can just return this value. If it's not there, it will compute the result and store it there. So this just means that if we ever call the same function twice on the same data, we can use a hash function to store that expensive computation rather than have to do the expensive computation every time. And so, for example, if you're doing video game pathfinding for whatever reason, you may want to trade some memory because searches are expensive. You're seeing that, right? With assignment 1, assignment 2, they're not very cheap. So if we say, what is the shortest path from this location to that location? Well, let's look up if we've ever done that before. If we have, just return the answer. And if it hasn't, then we have to compute it and store the answer. So someone said they had this exact example as part of dynamic programming. Yes. However, okay, I should use a different example then, because this is not meant to demonstrate dynamic programming, but it is unfortunately kind of how dynamic programming works. So this is applicable in many, many places that are not dynamic programming. And so I'm going to change this slide for next time because that's a little bit confusing. Oh, excuse me. Someone said, so it's a cache? Yes. So on the previous slide, I said it was a cache. All right. So now that we know what hash tables are used for, how could we actually implement a hash table? Well, let's just implement it as a 1D array. We're going to have contiguous memory. That's important because we're going to be looking through this hash table a lot. So we want the cache to be very friendly. Each index array, or each array index, essentially we can think of as a bucket in our data structure. And our job is to put things, data, into buckets, okay? So let's say that what we want to do is make a phone book. All right, so this is a phone book example down here. What we want to do is we want to take people's names, hash them, and then store their phone numbers in the buckets of our data. So we're going to take John Smith, for example. We pass John Smith through the hash function. We get the number 2. So we look up in the array index number 2, and we store John Smith's phone number there. Similarly, for Lisa Smith, we store it in 01, and for Sandra D, we store it in 14. Okay. So which value do we want to store in the hash table? Well, maybe and often we actually want to store the original input as a key value pair inside the hash table. So for example, when we take John Smith and we hash it, we may actually want to store John Smith's entire name along with the phone number, okay? And the stored values that we want to have depends entirely on the application. All right, so let's recall really quickly these hash function properties that we looked at before, okay? So just put this here as a reminder slide on that. Because now we have to talk about the hash table load factor. This is a great exam question. So the load factor is equal to n over k. So n is the total number of entries in the table, and k is the total number of buckets. So if the load factor is 0, then the hash table is empty. If the load factor is 1, then the hash table has something in every bucket, or it has a number of entries equal to the bucket. And in some hash table implementations, we can actually have a load factor greater than 1. Okay, and we'll see how that's possible. And typically, the performance of a hash table is going to decrease with increasing load factor, because as the load factor increases, the hash collisions increase as well. So basically saying the more stuff you put into a hash table, typically, the slower the hash table will be to use in the future. So hash collisions again. Bijective hash functions with table size equal to the input size have no collisions. So where I showed you mapping a 2D array to a 1D array, that's a very, very rare constructed case. That is not going to happen in practice when you're like constructing arbitrary hash functions. Typically, the input range is going to be much bigger than the table size. So that means, for example, if we're hashing strings to integers, and we've got a megabyte of data, let's say we have 1 million entries, well, there's way more than 1 million possible strings, right? So we're never, in practice, going to have this sort of bijective case. So a hash collision is going to occur when the bucket for a new table entry is already occupied. So mathematically, this is when the hash of one input equals the hash of another input. So what do we do with Sandra D? Okay, it sounds like an old movie or book title, right? What do we do with Sandra D? Well, Sandra D, when her name went to go put into the hash table, John Smith's name was already, or John Smith's value was already there. So hash collision resolution is very important. The strategy for resolution separates most hash table implementations, okay? So different types of hash tables are going to have different ways of resolving what we do when we get a hash collision. The simplest possible solution is just to overwrite the value. Sorry, John Smith, Sandra D wants her number in here. She's going to overwrite you. So if the bucket is occupied, overwrite it. How do we overwrite it? Well, there's multiple strategies for that. We could store the newest value, or maybe we want to store the oldest value. So storing the newest value would be saying, sorry, John, Sandra is going to be stored here now. Maybe we want to store the oldest value in some cases. So sorry, Sandra, John was already here. You can't have his seat, okay? Maybe we want to store the minimum or the maximum value. So if we're hashing like people who owe us money, maybe we want to overwrite with the person who owes us the most money, right? Or if we're talking about searches, maybe we want to store the deepest search result, or we want to store the value that we spent the most computation time on. And so this isn't used in practice because you can see very quickly that too much data is lost, right? We're looking stuff up, it's no longer there, and so it's really not used in practice. And if it is, there's some really strict conditions on what's overwritten, and it's just a nightmare. So we don't typically use this. Okay. Chaining is a very popular solution. Let me move myself over here so I can just see this. So for chaining, each bucket is not just an entry, but it's actually the beginning of a list. All right? So when inserting into the bucket, we are actually adding to the end of a list. There you go. That's chaining. So if a hash function is uniform, then each list should have the same size and it should be relatively small, right? In the worst case, if everything collides, then we're just going to have one huge list. And that's going to suck because it's O of n query time. So in order to find our entry, we have to look through the whole thing. And so the average query time is going to be the same as the average list size. And we could replace the lists with a set or, some other thing that's more efficient than just a list, but typically chaining is just done with a simple list. And because each bucket is a list, our hash table can grow way beyond the initial array size, right? We could have an array that stores like way more items than the things that are in it. So we could have a load factor with chaining that's infinitely larger. Well, not infinite, obviously, we have finite memory, but we could have a load factor that's larger than 1, which seemed counterintuitive at first, but if you think about the implementation of chaining, then it becomes a little more clear. Next, we have open addressing. So in an open addressing hash collision resolution scheme, instead of having lists, all of the records are actually stored inside the array. So there's no lists or external data structures. The way that it works at a very basic level, basic open addressing, is that when we have a new entry to be inserted, if there's no collision, then we're going to insert it into an index, right? So like when John Smith was the first one calculated, we just put his name into the list, or his phone number. However, if there is a collision, what we're going to do is we're going to scan forward in the array somehow. That has some rule, which we'll talk about in a bit. And then we're going to insert it into another open space into the array. And typically, open addressing is going to require a secondary key value or a secondary hash in order to look stuff up. So when we're looking up an entry, we're going to look at the original index, and if the second hash matches, then we return. Otherwise, we keep scanning forward with the given strategy until we find an entry that matches the second hash function. So the simplest way to do this is open addressing with linear probing, okay? So all we're going to do is we're going to look at the next bucket, okay? If it's empty, insert it. If it's blocked, go to the next one. When we insert, we need a secondary key or we can't do the lookup. And okay, so here's how we insert here. We're going to insert John Smith. John Smith goes to 152, right? That's pretty easy. We insert Lisa Smith. Lisa Smith goes to 1. We insert Sam Doe down here. Okay, no collisions yet. Then we insert Sandra D. Okay, so Sandra D hashed to the same value as John Smith did. So what's going to happen with Sandra D is we're going to go 1 forward because it's linear probing. So we linearly go forward by 1. And now we store Sandra's information in 153 instead of 152. However, then we have Ted Baker and we want to insert Ted Baker's information. Ted Baker just so happens to hash to 153. But even though no other thing hashed to 153, because of OA linear probing, now Sandra D is at 153. So Ted Baker gets inserted into, can't go into 153. Sandra is there. So we linear probe ahead to see Ted Baker, or to put Ted Baker in the next open position. All right. So how do we look stuff up there, right? Well, we're going to look at the hash index, and if the secondary keys match, then we know we found the value. If there is no match of the secondary keys, we go to the next value, and we repeat forward until the key is matched. So here, for example, we've stored a secondary key, which is the person's name. Typically, you'll have like a secondary integer hashing value. But let's say now we want to look up Ted Baker's information, right? Okay, so we hash Ted Baker, we find 153. We look up in 153, and we're using right here, just as an example, we're using the name as a secondary hash. So we say, does Ted Baker match the name here in the phone book? No, it doesn't. So we're going to look one forward until we do find Ted Baker. So we look one forward. Oh, we found Ted Baker. So we can now return that information. See how that works? Then we might look up Lisa Smith. Oh, we found the secondary one, Lisa Smith. So with open addressing, we need a secondary key in order to make sure that we're looking at the data. That's why we have a secondary key. So there are different probing strategies for open addressing. Linearly programming can suffer from clustering, right? And you can see here there's a big cluster around right here that can happen. And so very few dense clusters will result in slow lookups. There are other possible strategies. We could do quadratic probing. So each time we go forward, we increase the value, right? So the first time we go by 1, then by 2, then by 3, then by 4. The second thing we could do is double hash. So we have another hash of the name of the person, and we would turn that into an integer, and then that integer is how far forward we look into the value. And what these do is they help spread out entries to avoid clusters in the hash table. Oh, hey, I've got a visitor here. 1 second. Oh. This is Freckles. He's very vocal because he wants to get outside. Don't you, Freckles? So Freckles wants to learn about open addressing probing strategies. He's our outdoor cat, so I'm gonna let him outside real quick. So just give me like 2 seconds here. Someone asked, what's an outdoor cat? He spends most of his time outdoors. He just really sleeps inside. So we're kind of in the wilderness out here in St. Philip's. So he has a lot of place to go run around and chase mice and birds and stuff. Alrighty. So let's continue on. Coalesced hashing. Coalesced hashing combines the ideas of chaining and open addressing. So a chain structure is used on collision. However, the chain points to buckets in the table. And so it has better memory performance. However, we can only store the table size number of entries, right? And I'm just showing you this. I'm not going to go into the details of it, but just many different strategies that we can use. And on an exam, I would like you to know open addressing, linear probing, and chaining. Okay, so I could ask you about hash collision resolution with chaining or with linear probing. That's pretty standard. Okay, now game state hashing. How can we use this in AI, right? We often want to store relevant information about game states. So we may want to store the policy. So which move do we want to make? We may want to store a value or a heuristic about a state. And we can store that using a hash table. And some hash tables are trivial, right? Where states are simple. So often these will be tabular, like assignment 1 and assignment 2. So again, in assignment 1 and assignment 2, we know now how we can translate each cell on the map into an address into a hash table, and this will be bijective. So it'll be a perfect hash function, 1-to-1 and onto, right? So we know how to do that now. So if we wanted to store some value, like whether or not it's in the closed list, we know how to do that now. Okay. Here's a blackjack policy, right? And it's stored in a hash table. So the hash Jeez, 1 second. Excuse me. The hash table used here has your hand in blackjack as one of the entries, one of the, as the rows, I guess, and the columns are the dealer's hand. So we can hash things like this. Someone said, if we've got predefined policies, can't we use a lot of if statements? Yeah, but the point of this lecture is not if statements, it's hash tables, right? So here's how we can use hash tables in game state hashing. What about, okay, these are trivial, right? These are like 1-to-1 and onto. What about non-trivial state hashing? So for games with non-tabular structures, how do we compute an integer value for a state? One way is that for each game, we could come up with some custom function for each separate game, but that can be, really time consuming. And we have to ensure that the hash has really nice properties. And it may also be very expensive to compute. So I just wanted to talk about one possible hash function that's very popular among especially board games where you have pieces at locations. It's called a Zobrist hash function, and Zobrist was the person who came up with this function. It's often used in games. It ensures to some level a degree of uniformity. It is very fast to compute because it can be incrementally updated. So the actions in Zobrist can be, you can like take a hash state at the beginning of a game, and every move that you make, you can just make incremental updates to the hash function, which are very, very very, very fast. And hang on, I just gotta time out some trolls in the chat here. All right, I have zero patience for any trolls while I'm teaching, just to let you know. So this is going to, the Zobrist hash function is going to rely on two main components. It's going to have first a table of random values, and it's going to have the XOR operator. What in the hell is the XOR operator? So the XOR operator is going to take in bits, okay? And it's going to perform bitwise XOR. So when you have bitwise XOR, you're going to, the XOR operation basically says, are the two bits different? If the two bits are different, the output is a 1. If the two bits are the same, the output is a 0. So here, for example, we have A, which is 110101, and we have B, which is 010101. And so if we XOR these together, so 1 and 0, that they're different, so it's 1. 0 and 1 are 1, and the rest of them are the same, so they're all zeros. So A XOR B is going to be equal to C. That's what I've done here, okay? Now, if we look, XOR has some really cool properties. It's my favorite operator. XOR is actually Turing complete or something. I think or maybe that's NOR, XNOR, I can't remember. So XOR, any value XOR with 0 gives you the same value. Because a 1 XORed with 0 will stay a 1, and a 0 XORed with 0 will stay a 0. So anything XOR itself will be equal to 0, which is great. Another interesting property is that if you XOR anything with itself, you get 0 because everything's the same. So A XOR itself is 0 and A XOR 0 is itself. So look at this. This means that if we take A and XOR it with itself, then we get 0, and 0 XOR B is going to be B. So we can do some really cool things with the XOR operator. And XOR or A XOR B equals C, we can get back to any of those values by XORing with any of the others, okay? So this means that C XOR A is B and C XOR B is A. So if you take any of these two and XOR them together, you get the third one, which is really, really cool. All right, so the XOR operator is reversible, which is super, super cool. All right, so the Zobrist hash function, we're going to start with an initial hash value of 0. Next, we're going to generate a random integer for each board position. For each position, you're going to have a random integer for each possible piece that could be at that board position, okay? So, for chess, for example, we have 64 possible positions, and there's 12 different pieces that exist. 6 different pieces per color, so we have the 6 different pieces per color, 2 different colors, 12 possible pieces. So we're going to create a table of size 64 times 12, so a 2D array, 64 by 12. Each of these is going to be given a random value, right? We're just going to generate some random numbers and put them in there. And this random table, that random value means that this piece is at this position on the board. So, in order to put a piece on the board, you take the hash function representing the entire state, which is initially 0, right? And you XOR it with the random value for having that piece at that position on the board. And so that means, for example, right? Let's say we had random position piece. Let's say it's like, I don't know, A1, and we had a rook there. So if A1 rook had a value of like 0, 1, 1, 0, okay? Now we're going to take H, which is initially zeros, 0, 0, 0, 0. We're going to do XOR, so we get 0, 1, 1, 0. And so the hash value of 0, 1, 1, 0 means that there is a rook on position A1. Now, let's say if we have like D3 pawn, if we have D3 pawn, and maybe that value is 1, 1, 0, 0, and we XOR that with the current state, so we have 0, 1, 1, 0. We XOR those together to get 0, 1, 0, 1. Then the hash value 1, 0, 1, 0 means there is a rook in the bottom left square and there's a pawn at D3. Now, if we want to take a piece off of the board, right, then all we have to do is the same thing as putting it onto the board because it's reversible. So let's say here where we have the pawn at D3 and the rook at A1, well, this was the rook at A1 value. So if we take the rook off the board, we're just hashing it back or XORing it back with this, and we get 0, 0, 1, 1. And now we have the value for there only being a pawn at D3, which was the initial value that we had up here. Now, I'm completely oversimplifying this because these should be like 32-bit, 64-bit random numbers. So we Here, we could easily have hash collisions. But if you make these random numbers random enough and you make them large enough, you very rarely have hash collisions here. So what you can do then is you use this hash value as the index into a lookup table, and then you can store some data there about the current state of the chessboard. So that is the Zobrist hash function. It is super cool. I love that function. Now, let me show you just how cool the hash function is. I've already given you all of this information. So this slide contains some of the coolest information in all of computer science, in my opinion. Let's look at how we can use that to a cool thing. Let's say we want to do some data recovery, right? So you may have seen before some NAS systems or RAID drives or whatever. So let's say you have 5 disks, or you have 4 disks in this case. 4 of your disks have data on them, right? And you want to be able to recover that data if something crashes. So what you can do is you can have a 5th XOR disk. So you have any number of disks. Here I'm just using 4. It could be 50, right? But you're just going to have an XOR disk. So you introduce one more disk, and what you do for this XOR disk, it's also called a parity disk, because XOR is essentially counting odd or even number of ones, and that's parity, right? So 1 XOR 0, XOR 1, XOR 0, that's just a 0, okay? 0 XOR 1, XOR 1, XOR 1, that's a 1. So we XOR all these, blah, blah, blah. So for each bit on each of the other disks, we XOR all of the values together, okay? Now, if any of these disks die, any one of them, including the XOR disk, we can get back the data on all the other disks. So let's say my second disk here died somehow. So what I'm going to do is I'm going to go out and I'm going to buy a new disk. I'm going to put it into this system, and I'm going to take all the other data and XOR it and put it on disk 2. And what I have done is restored the original data that was on disk 2. You see how crazy that is? How simple that is, and how well it kind of just works? And that is like the very, very basic explanation of how these type of systems work. And so you could have like 2 disk redundancy, and you could do the exact same thing, or however many disks of redundancy you want. You can do it with XOR. But just by adding 1 disk, you can save yourself from any disk dying. And I thought that was like absolutely amazing, and it blew my mind the first time that I saw that. Cool. That's the end of the lecture. We are done for the day. If we go back to look at the schedule, as I said, the day that I am recording this live is a holiday. So please, if you missed this live, it's absolutely okay, because it's supposed to be a holiday. I just had this time slot free, so rather than do it tomorrow when I have meetings and stuff, I'm recording it now. And I'm going to post it up on the website for you to watch whenever. The official class here was on Saturday. So if you're watching this on YouTube, none of this matters. I don't even know why I'm explaining it again. Yeah, so that was hash functions and hash tables, and how you can use that on your assignment, for the closed list at least, to speed things up. And of course, we're gonna revisit hash tables and hash functions on the midterm. So thank you very much for tuning in. That is it, and I will see you on Tuesday.